Yay. Here, I'm gonna change it right now because it's super nice. Okay, I just want to make sure that's being shared. Okay, you can do it if you want, yeah. Here's how you do it. Displays. We're gonna rearrange them. There we go. Now it's on. Brilliant. Yes, infinitely better. Okay, but that's no, it's not. That's recording. This is sharing the right thing. And that way, for someone on Zoom, I will steal the mouse, I think, and that way I can engage the muting. Oh, I suppose we could, yeah. If anything is necessary, we can, I'm just gonna do this. Yeah.
Come on in. We have a couple of announcements before we continue the talk. But it would be great if everyone is here for the announcements. I'll give the first announcement that not everyone needs to hear, which is speakers and organizers. There is a dinner for us tonight, 6 p.m. at Appy's. If you're a speaker, organizer, or otherwise invited to the dinner tonight, we will just linger here and go there together. The rest of you are on your own to enjoy the bounties of New Brunswick and everything in New Jersey, should there be such a thing. Second announcement, the retirement dinner, the big deal is tomorrow, 6 p.m. at Dashin, an Ethiopian restaurant at 88 Albany Street, walking distance from here. For those of you in the know, it's near Old Man Rafferty's. For those of you who aren't, you have your phones, you'll figure it out. So we will just walk from here, 6 p.m. The last talk should end at 5:30, so it'll be an easy transition. And the final announcement that I have to make is after Heather Demarest's talk ends at 5:30 or so, we will, before we go to dinner, have time for a little more story time. You know what that means. And so we have Eddie Chen chairing the next session. Eddie, please take it away.
Well, I'm pleased to introduce Heather Demarest to take a talk on bringing the Mentaculus to life.
Well, it's a great pleasure to be back here, even if we are in the strange building. And it's so wonderful to be here to support Barry in his semi-retirement. I don't imagine him ever retiring from philosophy because that's just who he is, at least in my mind, is a philosopher. And at least for me, being able to study with him, have him as not just an advisor, but a mentor was hugely valuable. I am a very different person than I would have been had it not been for Barry. And he is still, I don't believe in Platonic forms, but if I did, he, for me, is the Platonic form of how to do philosophy well. Very, doesn't involve an ego, and it's always open, curious, and maybe one day I too will be as enlightened and informed and helpful for my students as he was for me, but at least that attitude is one I continue to strive to emulate. With immense gratitude, I'm very happy to be here. And I hope that this talk today is going to be a little bit of, building on some of the answers that philosophers get from statistical mechanics. Maybe there's more that we can say, and in particular, adding my little bit to what I take to be the Mentaculus project. So I'm going to briefly go through some of, growing up at Rutgers. I feel like my siblings will all know the Mentaculus really well. But for those of you who don't, I will give a little bit of an overview. And basically, I think thermodynamics, we have a fabulous reduction of thermodynamics to statistical mechanics. This is one of the beautiful things that has happened in philosophy of physics. but I don't see it straightforwardly generalizing to the emergence of complexity. So the thesis is that we need more fibrillation, it's a technical term. And I think that there's a nice way of kind of extending the project to include complex systems. So we go back, to some of Barry's earlier work on reduction. And this idea is that, we're trying to explain special science. So he says the non-reductive physicalism light still faces the problem of explaining how it can be that there are regularities in special science vocabularies that are lawful and which involve macro systems that are, from the perspective of microphysics, enormously complex and enormously multiply realized. How does it come to be that the particles and fields that constitute a special science system, toing and froing in conformity with the fundamental laws of mechanics, converge on lawful special science regularities? If there's an answer to this question compatible with non-reductive physicalism, then it must be that the answer lies within physics. That is, it must turn out that the laws of fundamental physics and the arrangement of physical facts entail the existence of the special science regularities that play the role of laws. So this is the project, right? We want to see if by using physics, we can get all these laws of special science. And this is in response to Fodor, right? Who says you can have all that token reduction, it's not going to give you robust laws that are explanatory. Okay, so we can think of systems as being microscopic. They can be described at the microscopic level or the macroscopic level. So we have kinds, right? We have electrons. We also have zebras, properties, negative charge, striped, and behaviors. And all systems have this microscopic description, but some of them also have macroscopic descriptions. And in some sense, the macro is going to depend on the micro, some kind of in virtue of. And ideally, these are consistent. So again, we have different kinds of dependence. I don't really care how we cash it out. We can think of supervenience or grounding or whatever. But there's this way that the different fineness of grain, you have different objects. So we've got, the table composed of its constituent atoms, and it has the properties, behaviors it does because of those. We also have a dependence of behavior, right? Dependence of laws. So a rabbit depends on its atoms synchronically, right? It's like composed of them. So we have that kind of dependence. But a fox population is going to depend on the rabbit population over time. That's a diachronic dependence. And that's typically what we think of as lawful, right? These special science regularities are this diachronic dependence. Now, you might think, hold on, rabbits and foxes are composed of atoms, right? So if we have the laws of fundamental physics that describe the behavior of the rabbit, and the laws of population biology describe the behavior as a population, there's got to be some kind of communication there, right? There's got to be some kind of dependence. So a question for anybody working in this, how are they related? So this is GPT's impression of what Laplace's demon would look like. I think it's pretty great. I love all of this artwork. It shows how I have no artistic sense at all. But at any rate, you can imagine we've got Laplace's demon. If he knows all the microphysical facts and the laws, he knows he can make perfect predictions about the behavior of all these atoms. Since rabbits go where their atoms go, he also, right, can make perfect predictions about those rabbits. So if you're in a limitativist, you're like, this is all we need. Get special science, that's some kind of epistemic thing. But there's another way you could go. You could believe in something like strong emergence. Here we might think of Cartwright. And here you say Laplace's demon's all good when it's just atoms. But once they get gathered together, like in a rabbit shape, the laws of physics are like, oh, hold up, I don't know what happens here. We got to talk to population biology laws. And then the population biology laws come in and they say, here's what happens, rabbits and foxes. So you can think of those as kind of inconsistent, competing, right? It's like patchwork. You have different laws at different levels. I'm not going to talk about that anymore because I've been trained by Barry. So when you think about weak emergence, you can think of like Fodor's non-reductive physicalism, what we have here is Laplace's demon could predict the behavior of each rabbit, and he would get the right results. But he could not derive like laws or counterfactuals, any of the special science stuff. Laplace's demon doesn't get to know. And so he says, these unimaginably complicated toings and froings of bits and pieces at the extreme micro level. Right? Think about how multiply realized the rabbit is, or worse, like an economy, of all the different ways of being money. And Fodor thinks the fact that they're all so complex in the level of microphysics, like how is that going to give you anything like convergence at the stable macro properties? How is that? That's big mystery, molto mysterioso, I think. So we get that these special science laws are irreducible. And this is the autonomy of the special science laws for Fodor. Now, if you go in for the Mentaculus, that's not ambitious enough. We should be able to say more. We shouldn't just say that these special science laws are mysterious, that the stability emerges for who knows what reason. So how does this go? Well, this says that the laws of physics describes the behavior of the rabbit's atoms. The laws of population biology predict the behavior of rabbits. Laplace's demon could predict each rabbit. And if the Laplace's demon has a little bit more information than just the exact microphysical initial state, then he can also derive the laws and counterfactuals for population biology and for rabbits in general. He's going to do that using what they're going to say is a lawful measure over possible initial conditions. So the special science laws are reducible. Now, you have this nice explanation in the same kind of way that the individual rabbits, their behavior is reducible to some specific microphysical state, and those laws, you get the behavior of rabbits in general. The lawful behavior of rabbits is reducible to the microphysics plus some things. Now, if we think of Lower's package deal, and this is going to be a little more relevant closer to the end of the talk, but the idea is that you have all these different laws of the special sciences, and they are characterized in like this vocabulary of science. So shout out, Craig. We've got this kind of better best system idea, that there are many different levels of description that we can use, many different ways of talking about Humean laws, and there are some that work really well in physics, some that work really well for rabbits and population biology, and that ultimately those special science systems, so this is where he goes beyond the better best system. You might think those are all just doing their own thing, and epistemically, certainly that seems right. But metaphysically, you might still want that kind of consistency, right? You don't necessarily want to be Fodor and say it's not molto mysterioso. You want to say how they talk to each other. And so here, Barry's going to say the package deal also requires that these special science systems can be unified, right? Into a system that's going to be constrained by the laws and the ontology of fundamental physics. They should all hang together. So the way that it all works, and I don't know if this is boring, if it's all just the same stuff that you've heard in class for many years. But we've got the macro state, which you can think of as something like a hot cup of coffee, and then a micro state, which is going to be the positions and velocities of every single particle within that hot cup of coffee, and that's going to have some very specific configuration. Right? So each particle has 3 components for position and 3 for velocity. So in phase space, you list them all up, and that gives you a single point. And so in phase space now, a single point represents the entire microstate of the entire system, every particle. So that means your phase space has to be very big, right? It's a 6n dimensional space. And regions in that phase space represent all the possible ways of being a hot cup of coffee. And you can think of it like you adjust the velocity of this particle a little bit that way and this particle a little bit that way. It's still at the same temperature because temperature is just average velocity. So this is the same temperature, hot cup of coffee, but like you can wiggle the atoms around a little bit. The same macro state, different microstates. Yeah? Okay. So how do we get thermodynamics out of this? Well, they're robust behaviors. We get these patterns at the level of thermo. And what you have is something like this. Gas, if it starts in the corner of a box, is overwhelmingly likely to spread out. Why? Why is that? And if you ask thermodynamics, they have a special, thermodynamics has a special science law that might say, in general, gases evolve to uniformly fill and take on the shape of their containers. So this was a law. You might have known this without ever knowing physics, right, or the underlying particle motion. You just watched filled a bunch of balloons, you have children. Like, wow, that's interesting. It always fills, I mean, they're stretching the shape. But the idea is that in general, right, it expands. You've got stinky kid that just came home from sports. You're like, wow, it really filled the room. Why is that? You're like, thermodynamics. Why is that according to statistical mechanics? Well, here's where the reduction happens. Continuously many microstates that kind of count as that initial gas in the corner of a box. That's like also a way of being in the corner is like this, and another way of being in the corner is like that, and another way is like that. And that will now be a region in this very high dimensional phase space. And then you look at what happens to that region, and most of the trajectories in that region leave the region to be in this region of being fully spread out within that container. So the initial microstates, you can then say that equally likely, and do a uniform measure, say all the ways of being in that corner, somehow just as likely as each other. And then the vast majority of those go on to be spread out. So you can say you have probability in, probability out. And so those initial probabilities propagate all on through. So you say, this is the very highly likely outcome. Yeah. So now you've got a beautiful statistical mechanics explanation for thermodynamics. And this is really hard to draw. I always think in pictures, so this is my attempt. But you can think like, here's the region in phase space of being in the corner. And being in the corner is, of course, a way to be in the whole box. So that's got to be inside the volume. And most trajectories that go through here will end up leaving the region. Numbers game. And the way the dynamics work. So what we have is maybe the actual trajectory through phase space. You can think of time as this dimension, right, as we move along. Here's the initial condition and the final condition. So you start in the corner, you end up outside, and then you stay outside, right? You are outside of the corner. You stay kind of in the hole, filled the whole container for a really long time. And eventually, the Poincare recurrence stuff, so we've seen you end up back in there at some point, but it's going to take a really, 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 really long time. Yeah. Okay, this is all familiar. Now, one big problem with this is that the laws of microdynamics are time reversible. So you get for the very same reason, you get all the same predictions towards the past. So not only is this trajectory overwhelmingly likely to leave and not go back in, if you think of something that's kind of half spread out, the gas is half spread out through the container, you wonder, what was it a minute ago? It's overwhelmingly likely it was more spread out rather than less. Why? For the exact same reason, it's going to be more spread out rather than less. So that's not good. You need to block that, right? So the solution, as Albert has defended at length, and very true, is the past hypothesis. And you put all this together and you get this big project, the Mentaculus. So this is famously from A Serious Man. I'm sure you've all heard that story. For the probability map of the universe. That's what this is. It's like one of the best names, right? You couldn't have chosen better. That's exactly what it is, a probability map of the universe. What does it do? Well, it's going to yield a probability for every formulable proposition. Bold claim. More restrictedly, we might say it yields a probability for every special science law. And that's what I'm going to be concerned with. So far, all I've given you any reason to believe is that it gives us probabilities for every thermodynamic claim. maybe not even that, for boxes, boxes of gas. And so we can combine these things. The dynamical laws are those of microphysics, SP is the statistical postulate, and pH is the past hypothesis. So you put those three things together, that's the project. Okay, so moving on. This is, I think, really lovely. It's such a cool view. I teach it to all of my students now, passing on the legacy of the Mentaculus. So I think it does a really good job at avoiding bad statistical mechanics retrodictions. It recovers existing statistical mechanics explanations for thermodynamic regularities. I think there are really good arguments that that works. They claim that it yields in principle, of course, not in practice, probabilities for every other regularity. So special science regularities from chemistry, biology, psychology, including things like how often to expect successful dinner parties or where spatulas are likely to be located in apartments. So how is it going to do that? Well, the story is that it's supposed to go kind of like it does for thermodynamics. Thermodynamics is the test case and it works really well. So you're supposed to just kind of generalize. Yes, and. So we have this, physics is the father of the sciences, keeping all their laws in line. But one of the special sciences is, in a sense, the mother of all the others. It plays a special role in unifying all of them with each other and with physics. That science is thermodynamics. Thermodynamics includes regularities that concern the transfer of energy, that relate macroscopic quantities like energy, mass density, pressure, temperature, radiation, frequency, and entropy. Since the regularities of the special sciences also involve processes that transfer energy, their phenomena are also covered by thermodynamics. So this is where I think it goes. I don't think this is right. I think that was too quick. So one of the ways to see that is to look at kind of the examples here, right? So suppose that an ice cube is haphazardly dropped in a glass of warm water, and then the system is approximately energetically isolated. So you can think of it as like branching off. Now you got your little system. And what's going to happen? Assume that it satisfies the second law. So it's enormously likely, you do your Mentaculus machinery, that there is no correlation between the microstates. So that once you've got this ice cube in the water, you can think of it as doing a new kind of initial conditions, right? You take that state of the ice in the warm water, do a new uniform measure, and then see what happens. And the past hypothesis is supposed to justify why you can do that. Now, the state is selected at random from the states that realize the macro state, and it follows it's enormously likely that entropy is going to be increasing. Okay, so there's nothing wrong with that. But what we see is that when you try to apply the very same logic to systems that are not ice cubes or not uniformly increasing, you get differences, right? So the Mentaculus implies that the entropy of the universe is enormously likely to increase from the time of the Big Bang. True. It also implies that the entropy of a typical isolated subsystem, not at its maximum entropy, is very likely to increase until the system is at its equilibrium. Okay, technically also true. And you can think of this like the ice cube in the warm water, right? Very likely entropy increasing microstate, since almost all the ways in which it can be formed are entropy increasing. Okay, so what's the problem? The problem is that when you look at biological systems like zebras, you notice that this is not always the case. So entropy does not, and you have to be careful about the sense in which it's not exactly the case. So if the system's sufficiently isolated, yes, entropy is going up and towards equilibrium. But entropy does not increase uniformly or monotonically throughout all these different systems in the same way that it does for thermodynamic systems. So complex biological systems, for instance, like we are really good at this, thank God, right? That we can maintain our entropy or even reduce it, right? When you go from being like an egg and a sperm to being a complex human with like a brain that, gets more, encodes more information all the time. I like, people like to point out that as you get older, this is maybe a favorite example that I've heard a lot, oh no, entropy takes over, but it really doesn't. Like your body is constantly fighting entropy. You're ingesting very, very highly organized food, excreting very disorganized waste, and that's to maintain yourself, right? It's to keep you going, entropy maintaining system. So many, many, many systems are like this. In fact, most of our special sciences are like this. So even if like the isolated, so you're like, okay, yeah, but Heather, you're cheating, right? Zebra's an open system, right? It's taking in highly ordered things and getting rid of disordered things. But you say, yeah, okay, include everything you need to do your closed system around a zebra, such that entropy in the whole system goes up. What you'll notice, even if that's on its way to thermal equilibrium, you're like, what do I have to get to have a closed system? Maybe you got to include the sun, right? And the whole solar system. And now the thermal equilibrium isn't going to happen for billions of years. So very different from like a box of gas, right? Where you start off and like thermal equilibrium is reached very quickly as the gas spreads out. So it's just not a very useful framework for trying to understand a zebra, because the best way to understand a zebra is as a big open system. Okay. So even, so Barry recently mentions how these stabilized regularities that we see are explained, right, by evolutionary history, right? At some time and for a period of time, it's likely that due to natural selection, the relative sizes of predator and prey animal populations in a region become stabilized. So the Mentaculus provides the probabilities that underlie this process. So I think that this is right. Like evolution plays a huge role in the selection of these kinds of systems. You don't just get them forming Boltzmann-Brain style in these timescales. They require a lot of selection. My claim is that the Mentaculus won't get you that, at least straightforwardly. So Barry claims that the probabilities explain why the toings and froings of fundamental particles converge on the special science generalizations like this one. So the question would be, how does it do it? Or how could we maybe supplement the Mentaculus to be able to do it? And I think it's going to be useful to contrast a few different kinds of cases. So I like to think of it as there's kind of robust, weak emergence. So don't worry about the word emergence. That's just the idea that we have these special science laws that exist. We can still go in for the kind of Mentaculus reduction here. Now, the way that these work is that the actual microstate is very likely to be in a typical state or in a state where most, right, the high uniform measure will have regular behavior. The gas spreads out. Now, of course, some of them are going to be weird, right? There are going to be a few microstates, even in thermodynamics, classical thermodynamics, where like if things are arranged just so, you have Maxwell's demon set something up, and things are going to go strangely. But in general, right, you can imagine like gas just bouncing back and forth. So it never spreads out because it starts in a weird place in here. But in general, measure one, they're going to behave normally. Now, that's just the standard story, right? Now, you can also consider the other extreme, something like chaotic weak emergence. So here we have something like strange attractors. And here there's very, very sensitive dependence on the initial conditions. So it's no longer that like, yeah, all ways of being in a box of gas are basically the same. Not when you're talking about butterflies and hurricanes, right? Like there's like one very particular way things could be that will lead to some very particular outcome. And so now this uniform measure deal is no good. Right? You have to know exactly the microstate. So the only way of predicting the behavior of these kinds of systems is by simulation or precise calculation. You can't do this statistical thing anymore. But now between these, there's kind of this fun middle ground, and that's where I think most of the special sciences are. So this, I would just say, I'm calling it complex weak emergence. I'm just like adding more words that philosophers hate. And it's only because I've been working with a bunch of scientists lately, so I apologize. But doesn't matter what you call it. The basic idea is that there's this middle ground between the robust thermodynamic systems, where pretty much anything is going to do it, to the chaotic ones, where there's very sensitive dependence on initial conditions, to these, where there are some, in some highly constrained region of phase space, that lead to the special science behaviors that you can expect. So things like zebras being chased by lions. And you can think like, okay, you might think that this region is anything that's kind of thermodynamically zebra specified, temperature, volume, pressure. These are maybe the ones that look like zebras, and then maybe within those are the ones even more specific that will behave like zebras. Okay, so small changes to the initial microstate are likely to yield something that does not behave in the typical special science way. So small changes, if you're talking about a box of gas, that's fine, right? You move this particle here, that particle there. This one's a little faster, that one's a little slower. But if you do that to a zebra, like scramble it up a little, it's not going to behave like a zebra anymore, right? You've taken it from one of those regions where it has the characteristic behavior and you put it somewhere else where it doesn't. So it exhibits this kind of bit of sensitivity, right? In the same way the butterfly hurricane does, but it's not quite as bad as the butterfly hurricane. Right? We can still use macroscopic things to latch on to those regularities. Okay, so how are we going to do this? We now bring in the Mentaculus. So let's suppose that the Mentaculus recovers all the right thermodynamic predictions. I'm just going to assume that by using statistical mechanics. And it successfully eliminates the bad retrodictions. The problem is that a thermodynamic specification of a zebra will make terrible predictions. If I just give you a thermodynamic specification of a zebra, it's overwhelmingly likely to be like zebra soup on the inside. It's like look at all the particles, like what measure, uniform measure over all the ways of having those thermodynamically specified properties. That's not going to have anything like DNA or organs. It'd be highly unlikely, right? It's like the old creationist arguments for why we were, we had to be designed. It's like, imagine a tornado going through a junkyard and assembling a jet. That would be so unlikely. So yeah, imagine statistical mechanics. You're just bouncing all these atoms around and they're all zebra thermodynamically specified. Overwhelmingly likely to not be a functional zebra. Okay. So what do we have to do then? You're going to make all kinds of bad predictions. You don't get your special science. So you might think, well, what are our resources in the Mentaculus? What can we do here? Because it's not enough. You'll remember initially the past hypothesis, a lot of the reason for positing that was so that you eliminate the bad retrodictions, but recover exactly the right predictions. So you might wonder, like, how are we going to, that's not going to do it for the zebra. It's not enough to just rule out the bad ones and reproduce the thermodynamic predictions, because we don't want the thermodynamic predictions. We want the special science predictions. So we need to do something more. So what else could be doing the work? So one answer you could say is the past hypothesis is actually doing more than that. So it's not just ruling out the bad retrodictions, it's doing more, right? You can actually appeal to it for more. And here's maybe one way that goes. Maybe there are just not very many trajectories that begin in a low entropy initial state and 15 billion years later have anything like zebra shaped soup bags around. Right? That would be like the Boltzmann brain version of the zebra. Like if you start in a very low entropy state and you say, now I've got a zebra looking thermodynamically specified thing, how likely is it that it evolved versus formed randomly? And it may well be that that's enough, right, to get you. It's actually pretty high probability that it's not soup bag. It's got organs or something. It's somehow able to survive. Another thing you could do is put it into the macro state and say, look, a zebra, you can't just specify it using thermodynamics. You got to bring in more machinery. You got to now talk about other things that might be going on there. And another thing you could do is say, yeah, you specify the zebra thermodynamically, but then you have to conditionalize on a bunch of other stuff. And so that's the Mentaculus only tells you what thermodynamics you should expect. But you can bring in other knowledge, right? Like maybe conditionalize on everything you know. Okay, so why isn't the past hypothesis going to get us everything we want? Well, for one, you can have all these kinds of convergent evolution facts. So you might get that it's overwhelmingly likely that a zebra-shaped thermodynamically specified thing evolved, and then it's likely to have some kinds of functional behaviors, like maybe you'll know it's going to maintain its entropy, but you might not know about its DNA, right? It's not going to get you that for sure. So maybe there are lots of ways of encoding information that allow things to persist. So maybe we turn to the macro state. I mean, it's not enough to specify it thermodynamically. So here, we've got some Albert quotation. Here's some suggestions, right? Maybe the macro state has to do with our everyday human language, our discriminatory capacities of unaided human sense organs. And then the claim is that those coincide with a simple, autonomous, robust, non-trivial dynamical science of thermodynamics. So I think, for one, I don't know that, I don't know, are those the ways that you experience the world in terms of temperature and pressure and volume? It's like, I don't know, what's color here, or any of the other ways that we perceive, right? So you might think the discriminatory capacities are already getting us more than like the properties we appeal to in thermodynamics. And so I think one of the questions here is like, to what extent do they actually coincide? And to what extent do unaided sense organs go beyond thermodynamics? Okay, so I've already said that. So let's see, there's no issue, I don't think, in allowing that some kind of Laplace demon could like know which microphysical states, realize which special science properties are. So you might think initially there's a kind of translation problem, and this is one of the things Fodor was really worried about, that you couldn't read in the microphysics, like which things were rabbits maybe. But you know, if you look into the Mentaculus to tell you which things are rabbits and which things are not, I'm not sure it can do that, right? Because I think on this view, it doesn't fall out. It might be the kind of thing that you have to add to the macro state to constrain it, right? To then ask about it. So if you just use your like sense perception, and this is now maybe more in line with what Barry wants to do with the package deal and the different levels, right? That like there's no fundamental properties, perfectly natural fundamental properties, but properties at every level. Then you might think we'll get all these good results, like you have to conditionalize on the fact that zebras have eyes and stripes and tails. But again, there are going to be many, many more ways that you can have a zebra soup bag consistent with all the things you see with your unaided human sense organ. And most of those are going to go straight towards thermal equilibrium. So you might think you just like conditionalize on more stuff, right? You add more stuff into the measure. And maybe this is going to be easier to just see in the pictures, because I realize time. Okay, so one thing I just want to flag is it's not just living things. There are lots of systems that seem to exhibit this kind of divergence from thermodynamics, where you might not expect it to produce patterns just from a uniform measure over which things are likely. And this is what's led to some of the thinking about complexity that I've been working on lately. There are different ways of, and different sciences especially have different disagreements about what counts as complex. But the basic idea is that when you pick out these systems in phase space, and you pick out your volume, and you think, all right, where's the zebra? You can do it thermodynamically, and that's too big of a region. What we need is something like a tiny fibrillated proper subset of that region. So that's gonna be much smaller. Okay. So let me see, here we go. And then maybe I can go back, but the idea here is that the ones that count as zebras, you could just do a uniform measure over those. And maybe that will give you all the right special science results. If you restrict your attention to those microstates that have DNA, that have all those other properties that we think of zebras as having, then you do a uniform measure, that might get you, right, all of the special science regularities. And you can see, right, the typical behavior just doesn't take them out of that region. They stay as zebras. They don't spread to fill their container. Okay, so where are the rest of my pictures? Well,
Backwards.
I'm out of time anyway. I apologize. I did not judge the time right. So the basic idea here, I'll give you the equation. Maybe that'll give you something to chew on. So the basic idea is that if you take the thermodynamics, so the reduction of thermodynamics to statistical mechanics is hugely successful. And the idea of doing the past hypothesis to get rid of the retrodictions that are bad, but keep all the good predictions, I think is great. The problem is that if you just are reproducing what thermodynamics would say for a region in phase space, you get all the wrong predictions for special science. So you have to do more. The Mentaculus, as it's often presented and understood, just doesn't do enough. So question, what more can we add to the Mentaculus picture? You could say it's all being done by the past hypothesis if you think about it carefully enough, and maybe you will get some benefits by doing that. Another thing you can say is that the macro states that we take seriously, those are the things that need to be modified. And when you properly restrict the macro state and do a uniform measure over that, you get all the right predictions. Another thing that I think you should say is this, that you say the thermodynamically specified region is the macro state, just like we always did with thermo, but that for a zebra, the space in it that are the good states are very fibrillated, right? There are just a few of them in there that will have the right predictions. Those are the ones on the trajectories that are going towards special science regularities. And that ratio, so the proportions of volume actually give you a cool measure for how complex a system is. Because if there are fewer, right, the fewer fibrillated states that count as zebras within the thermodynamically specified one, that would include all the zebra soup bags, that ratio, the smaller it gets, the more complex you might think of as the functional, and the more complex the thing is, or the higher the informational complexity. So this is kind of a way of linking up what some people are doing for how much functional information a system has with a project like the Mentaculus. So it's kind of like a translation device. Like, how is it that we can use this ratio in a way that I think respects and dovetails nicely with some of the other stuff that Barry and David have already put. So thank you.
We had a good talk, but time for discussions. Okay, how about David start? And please keep your hands up. Hands up.
Thank you, Heather, and I think there's lots of interesting questions being raised here. Yeah, I guess I probably have way too many questions and comments to say, but let me just pick a few. One thing is, I'm not sure, yeah, there is this idea floating around that once you have thermodynamics, then everything else will supervene on thermodynamics. Probably Barry has been more enthusiastic about that idea than I have, but there's also just a question, there's a little vagueness about what thermodynamics means.
Yeah.
If what you mean by thermodynamics is assigning a density and pressure and temperature to every coarse-grained point in a volume, where coarse-grained is on a fairly, to the smallest macroscopic scale,
Yeah,
then a zebra-shaped bag of soup isn't thermodynamically the same as a zebra. I mean, the
Yeah.
various internal organs have different densities and pressures, and you're gonna be able to outline the organs if you know that. But having
Yeah.
said that, on any reasonable notion of what you mean by thermodynamic properties, I agree that you're not gonna get the DNA.
Yeah.
And stuff
That's
like that, but I think the soup stuff is
yeah, fair
is
enough.
probably
Rhetorical
exaggerated.
approach, yeah, that's fair.
But one other thing that's maybe worth pointing out, just in a very preliminary way. You said, look, the Mentaculus shows you why the total entropy of the universe is going to go up, and it also shows you well enough why the entropies of subsystems are going to go up.
Yeah.
But in biology, we're faced with entropies of certain subsystems going down. But come on, put a cold body and a hot body into thermal contact with one another. The entropy of the hot body is going to go down. Okay.
Yeah.
That's just straightforward thermodynamics and statistical mechanics. Okay. And in some sense, you can explain this by saying, if you put a cold body and a hot body in thermal contact, the most efficient way to increase the entropy of the whole composite system is going to be to have the entropy of the hot body go dramatically down.
Yeah.
So it's not like it isn't like until we get to biology,
Yeah.
we're not
Good.
familiar with circumstances where the entropies of subsystems, of non-isolated subsystems are going down. We see that all the time.
Yeah, good.
Okay?
Yeah.
And anything that even makes a claim to explain thermodynamics had better be able to explain that.
Well, good.
Okay.
Yeah, so I wish that this had shown up in like one of the books on this Mentaculus.
Well, fair enough.
But no, I think, so the points you raise are excellent, and this is part of why I really want to bring the Mentaculus to life. Because I do see this as a continuum. I don't,
Right.
I'm not
Right.
saying anything like, oh, entropy is on holiday or whatever. But I do think, there's something kind of distinctive. So in part of this project is, we're arguing that there's, systems tend towards more complexity over time.
Right.
That, like at the beginning of the universe, it's all quarks.
Well, presumably,
Eventually,
the
of course, it
complexity
away.
goes
Of course.
up and then it goes
Of course.
back down.
That's right. But
So
you
they
might
don't
wonder,
But
what
look,
explains this?
that you've got with a hot body and a cold body.
Yeah, well, let me get a cup of coffee and a cold glass of wine. We'll see if we get a zebra.
Okay, but
I mean,
just
but
one more,
yeah.
one more thing. You were acting as the sort of angle here seemed to be, look, the Mentaculus was developed in order to explain thermodynamics. But thermodynamics is not going to explain zebras.
Yeah.
And so we're in trouble,
Yeah.
okay? But that's not exactly the way I would have put it.
Yeah.
I would have said, look, we've got good reason to believe, we've got a really strong argument for the plausibility that the Mentaculus explains thermodynamics. Then there's the following kind of jump, okay? Absent reason to believe the contrary, you say, why is this probability distribution over initial conditions succeeding in explaining thermodynamics? Hypothesis, maybe because it's true.
Yeah.
Okay, and if it's true, then necessarily it explains zebras and so on and so forth. If the laws are true, you're going to have to work a lot harder. You're going to want more detail about lots of these cases, although of course you're never going to get perfectly anywhere close to perfectly fine detail. But yeah, I think you raised an interesting point. Suppose somebody says, suppose the past hypothesis is true. Suppose that you start out with a uniform probability distribution over the microstates compatible with that macrostate. And then somebody just gives you the very crude information.
Yeah.
You've got a zebra-shaped object,
Right.
16, and maybe it's walking around a little or something like that. yeah, claim, or I don't know what, maybe there are many ways that could happen.
Yeah.
Maybe you have to restrict it a little more, but claim, there's gonna be not too much of a restriction. Before it gets to be the case that the Mentaculus says, there's probably DNA in there, okay? Or there's probably some hereditary way of
Good,
encoding
yeah,
information.
Right, right, right.
Or
I
something
agree.
like
I
that.
mean, I feel like you're just agreeing with me. This is,
Sounds good.
I mean, I think that, just a couple of quick things. One, I don't know. So of course, there's this idea like, if you're right, the project is, there's the uniform measure and the low entropy state and deterministic microphysics. And it better work out, like,
Right.
well,
Well,
yeah.
no, we've got a plausibility argument that
Totally,
works
yeah,
out
yeah,
the thermodynamics.
Right.
And then you
But I
sort
also
of
see the
say,
plausibility argument that the thermodynamics thing doesn't straightforwardly apply to zebras.
Yeah,
Why?
but that's
Because a uniform measure over a thermodynamically specified zebra doesn't make good predictions.
no, but that doesn't mean that the uniform measure over initial microstates doesn't make good predictions.
Right, well, that's
Initial
what I'm saying,
microstates
so
are
that's what I would need, that's what I think would be a beautiful thing for somebody to work on to like fill in
Right,
this
good,
explanatory project.
Good.
And how much do you get out of the past hypothesis alone with the thermo macro? Or how much else do you need? Like, do you really need the full observable macro state? Or do you need everything you know? Or what else needs to be conditionalized to get all the special science regularities, like that they have DNA, et cetera?
Barry?
So you kind of said this in the way you were doing it, but you also made the presentation look like the Mentaculus, great idea, but woefully incomplete. And you presented it in such a way, David said some of this,
Uh-huh.
as though the idea was you're going to get everything out of thermodynamics. But nobody ever thought that.
Should I get your quote again?
Yeah, you've got quotes.
That's not right.
Yeah. Well, he just said you can, and you're saying you
No,
can't.
you can't get it out of
No,
thermodynamics.
you can't get it out of thermodynamics.
Right.
You
But-
can,
but you said that
if this, if
thermodynamics
the
is
Mentaculus distribution gets you thermodynamics.
Yes, then it's plausible that
That it's
okay,
true,
when you
right.
conditionalize on a lot of other stuff.
Good, yeah,
Okay, but of course, that's what the whole idea from the very
great,
beginning.
yeah.
And the thing which got a little bit confused here, I think David said, I was enthusiastic, I'm not that enthusiastic. But this idea that if you're very coarse grained.
Yeah.
It's like, a TV screen. You get a pixel thing, you get things moving around, you see things. So we knew the density in very little areas, the frequency of radiation in very little areas, the temperature and so on. We get a lot of information, we know where things that look like rabbits are moving around.
Yeah, I mean, so this is, I think, a really interesting question. What does it mean to have a macro state only specified thermodynamically? So I think
Yes.
if I said temperature and pressure because it's what we do for boxes of gas, but you're right, if you go, and it's also has to dovetail in some other ways with other, I mean, I don't know how much we need to be consistent, but if you think available to the unaided human sense organs, now you can't go super microscopic to get little tiny partitions. It's also true that a dead zebra would have all the same thermodynamic
What you said last
specifications, but would behave very differently.
No, come on, a dead zebra is gonna have completely different fluid velocities in its arteries than a live zebra is. That's, I mean,
All right, how about
the
a
stuff-
sick zebra?
the stuff about zebras, stuff about zebras is really exaggerated.
When you're sick, you have an upset stomach.
Okay, so let me put it this way, if we want to pack all of that into what it means to give a full thermodynamic specification of a macro state, then I do think you get way better predictions and you could get a lot more out of a uniform measure. And then it would be plausible that the past hypothesis's only job was to rule out the bad past retrodictions because the future ones are guaranteed by a full thermodynamic specification. I guess I was thinking that you don't get it all just with that the past hypothesis may be doing something more. And that was that you would end up with an evolved creature with DNA.
Okay, so it was this business about this coarse graining, getting everything that
Yeah.
was, maybe that was a red herring, somebody.
Okay.
Okay, the main idea, and David sort of said it, so I'm just gonna re-say it. The main idea is that, look, you got this probability distribution. Now you just conditionalize on things.
Yeah.
You'll get things, but now what do you conditionalize on?
Yeah,
Well, that's the big question. That's the
Yeah.
program, and that's what sort of what you bring up.
I think that's another way to put
But
the
that was
problem.
there from the very beginning. It wasn't like that was a hidden thing. I think, I mean, you heard this meeting.
Well, what you need to be able to do is conditionalize on something that appropriately fibrillates the region. So it restricts it to the very precise
But-
ones that will have the right
I mean,
behavior.
in different, depending on which thing you're interested in, yeah, you conditionalize all sorts of different things.
Just ask a point.
Oh, okay, can I put it on a queue or?
I just wanna ask a question, an informative question. Is it or is it not part of the Mentaculus that what you conditionalize is something we call a macro state?
No,
No, oh, you can,
You can conditionalize.
Anything at all.
Conditionalize
You
on
can do the whole-
anything you want.
conditionalize on the micro state.
Conditionalize on anything you
on
know.
the DNA structure. of the
Yes, and you conditionalize
On the
micro
precise.
states.
Yes, of course. I mean, if you conditionalize on the precise microstate of the universe.
Okay, all right, so I'm losing control, and I'm thinking, okay, I have Allison, Craig, Mike, Michael, Dan, Tim, if you're on Q2. Let's see, Barry, you have the exemption from the rules, but if you want to
No,
follow.
okay.
Okay.
You know, I really like Heather's thought, but I did think it was a little bit like, what to say, what I said before, that you're just trying to make it say that the idea, there may be problems with the Mentaculus, because the probability issues may not be true. Or it might be, someone might say, look, you can get thermodynamics from a lot of other probability distributions as well. And if those probability distributions give different predictions for other things like baseball games or something like that, then maybe the argument from, look, we have reason to believe a probability distribution because of gets thermodynamics right, so therefore such and such about baseball games wouldn't be good. That's right. So there's still, it's very much open question about this, and a lot of it has to do with how you want to interpret probability, because there's reason to think, you think of probability in terms of the spread system idea, that the simple probability distribution is that's what we mean by probability. And so if that's what we mean by probability, then the predictions that it gets for the baseball games would be the right probabilities.
Yeah, so I recognize that there are other issues with the Mentaculus, and those probabilities are live questions, which measure to use and all that. I think the problem I'm trying to, I don't even know that like I would call it a problem so much as just future research that needs to be done, which is how to take this thing that works, I think, quite well in going from Mentaculus to thermo to systems that don't uniformly monotonically go towards higher entropy, right? So most of the thermodynamic systems in general go very quickly and uniformly towards higher
So
entropy.
you would put it by, what do you have to conditionalize in these
Yes.
particular things? Yeah.
Yeah, and also how much, and it's a little bit confusing way, like dialectically, because I don't know how much we get just out of the past hypothesis and a thermodynamically specified macro state. I don't think we get it all, but we might get quite a lot, right? Like you get some kind of evolved creature of some kind, but maybe not that it has DNA as opposed to some other way of encoding information and reproduction. And then, so what else needs to go into the macro state?
Very
What else
chancy
do we need?
things happen along the history of the
Right,
universe,
it's a hugely
which
contingent
might
science. Yeah.
be predictable from as really, you know.
Yeah.
As long as, very, very small micro.
Yeah, exactly,
Of course,
exactly.
yes,
Well, but so of course, but like it needs to show up somewhere in the framework,
of
right?
course, but that was
Yeah.
there from the very.
Well, but this is exactly what I want to know because I'm getting like kind of different answers. Like, is it the past hypothesis that gets you this, or is it additional information that we just bring because we happen to have used a microscope and written down in a book that it has DNA? And we can trust that because of a record, which ultimately might go back. So there are like a bunch of different ways you might go about trying to incorporate that information. I have yet to be convinced of some single thing that you both agree on is the right way to do it for something like a zebra. So this is me just saying there are certain dissimilarities, certain things that are different between zebras and like boxes of gas, where the arguments that are traditionally used for why this works so well for thermo don't seem to me as obviously to apply. And so that's why I think, and maybe different things need to be said in different situations, but I feel like more should be said, more can be said. Maybe functional information is a little part of that puzzle. Yeah.
All right, I'll be more strict now. Allison?
Yeah, I'm sorry, this is on a similar thing.
Yeah,
but
I
I'm
figured.
Quick now. So I guess the way I thought about reduction and unification was you have your lower level theory, you have some bridge principles,
Mhm.
and then you have your sort of high level stuff. And I always thought that in the case of even thermodynamics, you know, you had bridge principles, and it's very simple ones. They're about, you know, here's an ice cube, it's roughly like this, here's some water, it's roughly like this. But you still needed them.
Yeah.
I'm not sure Barry and David were always super clear on this, but you know, I don't think there was ever an aspiration to the Mentaculus alone to get you thermodynamics, because there are quantities featuring thermodynamics that won't appear in the low level theory at all. So this is why you need these bridge principles. And I guess I would have, I mean, here's my comment and then a question, an actual question. I would have framed it as something like, tell me more about the bridge principles in the case of more complicated sciences like biology and so forth. And I guess my question is something like, I think the complexity stuff is kind of cool. Is there a reason why though to jump ahead to these systems like life systems where, yeah, if you ask a biologist, you know, tell me what a zebra is really,
Yeah.
I'm not sure they know either.
Yeah.
You know, but in the case of physics, because we've been using kind of macroscopic stuff to study the micro level world, I think we'll have a much better handle on these kind of mappings between the micro and the macro. And so I guess my question now is something like, would you feel okay operating at a level of like explaining how we investigate the microscopic world using macroscopic stuff as a kind of mid-range case? Or do you think that it's important to start with the more complicated life case as a sort of way into this project?
Yeah, I mean, a lot of really good questions there. I feel like,
Sorry.
no, so the bridge principle, I was just kind of taking for granted that there was, you know, some way of, you know, I just assumed that we could pick out thermodynamic properties without any trouble and read it off the Mentaculus or off in phase space. But partly that's because I focused on temperature and volume, and those are like kind of very easy, right, to see how they show up in phase space. So just saying what the temperature and volume of a system is, that like literally translates into a region in phase space, right?
Translates weird. I mean, even in the case of, sorry,
Because temperature is average velocity and position gives you volume.
I guess I'm used to talking to people who are very interested in kind of the reduction between StatMech and thermo.
Yeah.
And even they won't say that kind of it's just there. You know, you have to tell me what kinetic, you know, you have to tell me about mean square kinetic energy, you have to kind of do various identifications. And I guess, you know, these people are really invested in kind of recovering the kind of things that scientists do when they reason thermodynamically, which is not quite the thing that the Mentaculus is doing anyway. So sorry.
Yeah.
Yeah, I mean, so maybe there are other reasons that even that case isn't as simple as I had thought. I just wanted to say, you know, the uniform measure for these very simple cases, very straightforward. I see very clearly how it works. Or is supposed to work. For cases where it's not uniform volume, but like highly fibrillated, there are only a few particular ways within that region that count as a zebra. One thing you can do is just say, yeah, well, give me the bridge principle. If you tell me what arrangements are like realizers of the zebra, we're done. Just do a uniform measure over like those 5 things. You know, those ways of being a zebra, micro realized in like the weird kind of way. You know, you get things organized just right. Maybe they're more than 5. But it might also be that now it's not a uniform measure, right? Like, I mean, so there are other things we might worry about. And then whether or not those can be macroscopically identified or like picked out metaphysically is my question, right? Like which like macroscopic things, like the, you know, the like unaided human sense organs, or is, you know, the other things that we have to now translate into what it looks like in phase space. Anyway, there's a lot.
More questions.
Yeah.
Great.
Okay, I just want to clarify what I think is the logical geography here and make a couple comments. So we've got the Mentaculus, the good old regular Mentaculus. And then now we have this add-on that all the special science laws are coming through mediated through thermodynamics.
Yeah,
So we got the father and the mother quote.
yeah,
And so it seems like there's two questions. One is whether there are illegitimate children. And then one is whether the children are behaving badly.
yeah.
So these would be special science laws that don't go via thermodynamics, and then ones that are thermodynamic but don't behave, the special science way.
Yeah,
And so it seems to me, that there are many illegitimate children. So that if we have, if we think, well, we could be more or less generous with what we mean by thermodynamics. So I would be more generous, maybe not just restricted to equilibrium thermodynamics, but non-equilibrium thermodynamics.
Yeah.
And all sorts of other things, but still, there's gonna be cases, there's gonna be generalizations in astrophysics where gravity is dominant and maybe nothing thermodynamic really, is right. There's gonna be things with the, cluster generalizations with chemical clusters that also DNA. And so there probably are, then I think of all the delicate contrivance of things that have to go right for a thermodynamic description to hold.
mhm,
And so it seems to me that probably there are a lot of illegitimate children. But then there's a question about, which may be more interesting, about whether some of the legitimate children are behaving badly.
mhm.
And so then, certainly you could imagine cases, and actually with DNA, you could imagine one where you could think, sort of generalization that DNA is always coiled.
Yeah.
Right-handed, but a left-handed coil would be entropically the same, I believe. Now there though, they will have more resources because they can say, well, this is like a kind of accident that it went one way rather than the other way. And it got stuck like that. And so then there'd be so I think there'll be more interesting questions then about whether the legitimate children are behaving badly and what the stories there are, because they will have a lot of, many resources in terms of, just think of things getting stuck, the kind of energy landscape might be very complicated where things again get stuck. Anyway, I just want us to, given that there are, I think, illegitimate children, I'm still wondering why posit this idea in the first place that things go via thermodynamics. So maybe that's a question for you, but also noticing that Barry's in the whole room.
Giving this talk, I was mostly just trying to say more can be said here. And so I agree that you've pointed out two like really cool further ways to be specific about how the limitations of this kind of picture. I don't know. Do you want to?
But illegitimate children? You're supposed to think of your students, your PhD students.
I know, I definitely didn't toe the line. I'm trying, I see this as a very friendly talk.
Since you asked, for me, the way this happened, it did happen, as you said in the talk. The photo had this thing, which made it sound like in order to besides special sciences, you gotta do something much more than physics.
Yeah.
And physics just won't do it. And I think Fodor didn't realize that part of physics included the probability distribution, which got you thermodynamics.
Yeah.
And my idea was, well, you add that, Jerry, and you get a lot of what you want. And in fact, I think you can follow a program in which you can get good kind of counterfactuals out of that. And because you get counterfactuals, you get things that, you don't have to go to the whole spiel about all of that. And I don't see that anything you say, and I think you agree with this, but I'm not sure, goes contrary to that. Now, Craig did, and he and Jonathan, did seem to say.
We disagree with you guys,
That you really disagree. Okay. But I didn't know where you could be then, whether you ended up disagreeing with the thermodynamic probability distribution, or you thought that maybe. Let me just say, and I'll shut up and let you say. I agreed with part of what you and Jonathan said, and that is not anything counts as special science. You gotta pick up vocabulary where you find interesting regularities that are relevant, that you find relevant. And that's what you would find the best system there. But when you get the probabilities there, you're gonna use this is mechanical probabilities, I think.
No, we were trying to figure out, when people talk about the autonomy of the special sciences, we wanted to, it seemed like a miracle that, the biologists who never even talked to a physicist whatsoever, when they best systematized their regularities, happened to get something that was exactly what the physicists came up with. Given all the different notions of simplicity and strength and all that, especially if you're putting some pragmatic things, that it seems even more miraculous. Now, of course, I think that the Mentaculus, you can conditionalize on anything, and you're not gonna get something. You can get back whatever you want. But the question is then, whether, then it seems that there I agree with Heather's intuition, I think, which is that, it works nicely in thermodynamics, but then it's like a kind of leap of faith. Or so seems more metaphysicsy, a leap of faith thinking it's gonna work for all counterfactuals and all of that.
All right, we have to move along the queue. To Michael.
So it seems like everyone sort of agrees that you have to add something to thermodynamics to get some regularity about zebras, something about the macrostructure of a typical zebra. And it seems to me the question really is about how much of the explanation of that regularity is in the stuff you add and how much of it is in the thermodynamics. Clearly you need the thermodynamics, it's definitely doing a fair amount of
It's
work.
a yes
but
and.
How much extra work is being done by the stuff about the zebra? In particular, how much stuff about the zebra macrostructure is helping to explain why you even see these high level regularities at all? Why isn't the world just kind of thermodynamically legitimate chaos? Why is it these highly adapted biological systems? I think your view is that a lot of the explanation of those regularities, and that really I think is Fodor's question, is coming out of these specific details about these particular macrostructures. And that's not to diss thermodynamics as an essential part of the explanation, but to say that it falls far short of really resolving Fodor's.
But everybody thought that. I wasn't disagreeing with Fodor. The thing that Fodor seemed to be saying is that you really have to add something more to the probability distribution. Not that you have to add more than thermodynamic description. Everybody thought that thermodynamics isn't going to get you the special sciences. But it's that the probability distribution, which gets you thermodynamics, will also be able to get you everything else. Because, I mean, just like you just think the fundamental microphysical state of the world will get you. You're shaking your head, but it sounds like I'm not very living.
So Fodor's question is, Fodor's question is why do we see these very high level regularities that are so much more general and abstract than anything that is
So
sort of
why there are any
statistical
regularities
pieces
at
right
all?
now?
I wonder sometimes whether just the past hypothesis and the details of the early macro state might have entailed that for a period of time there'd be macro regularities. I don't know that that's true. Someone like Sean probably is in a better position to say something. Cosmological question. He was doing something else.
Inconveniently, I think so.
But Heather,
Would you like to now?
Let me finish the thing.
Okay, so just let me know what happened.
Would you like to respond to
So I don't think I disagree with anything that
All right.
Michael said.
all right, good. Dan.
Totally naive about all this thing, well, bear with me, but I just don't understand why, if you include interactions between constituents in your gas. And you include the fact that they have to obey thermodynamics and other interactions. You just take evolutionary thought from biology, you get, maybe not, you get all sorts of things.
Yeah.
Some of them actually turn out to be living.
Mhm.
And when you're living, then they turn into other things. One of them, in our case, is zebra.
Yeah.
We've just been discovered a planet somewhere else that may have life on it.
Yeah.
We may not have zebras.
Yeah.
But I just don't understand.
So, I mean, one of the nice things about this view, I think, is that everything's consistent, right? So it's not like you're gonna discover some, like, this is where I would maybe push back against like Cartwright or even Fodor a little bit, but say, it's not like there's a law of biology that's really doing work that isn't kind of also in some sense being done by the physics. So like you have these, you know, everything in some sense can be explained by the microphysical determinism. And because thermodynamics is true, it's also part of the story at the level of thermodynamics. Now, if you're like, that's all we need to get all the predictions out, I think there's, like you're noticing, there's like a lot of contingencies. There's a lot of things that are selected for, like that end up making a big difference in this kind of long history. So I don't know that I latched onto your question.
If you're looking for a lot of zebras, that's gonna be pretty hard.
Well, we have lots of them, right? Like all the special science laws about zebras, about their DNA, and they graze and they have babies, they have stripes.
Yeah, no, you can get a description, but, yeah, but you can't get a lot of it pretty from the beginning of the Big Bang that you're gonna get zebra.
Yeah, it would have a very low probability.
Yeah.
Yeah,
But it's not zero.
yeah, that's true.
Isaac.
Thanks. Okay, so just for the historical record, one of the phrases that comes up a lot of time and chance is the directly surveyable macro state.
Right,
And the only micro conditions that are appealed to are stuff about the person's brain.
right.
So I think given that reading, I find it very persuasive and aesthetic to have it.
Well, thank you. Exegesis, yeah.
That's one comment. Another comment is, I don't know if you would like this way of putting your line of thought, so I was curious what you think. So there is, the past hypothesis picks out the initial macro state using only thermodynamic vocabulary.
Right.
But then when you're conditionalizing, as I'm understanding Mentaculus, you're not only conditionalizing on what I would have called thermodynamic vocabulary. There's other vocabulary in there too.
Right.
And is part of your point something like, maybe we should have expected that to pick out the appropriate initial macro state, we needed to use that other vocabulary as well, or it's quite surprising that we're gonna get the correct theory of counterfactuals, et cetera, by only having to use that other special science vocabulary, like sort of further downstream. Is that what you're? Is that a way?
Yeah, I think that would be a way to put it. So maybe think of it this way. If you know, if I conditionalize only on thermodynamic facts that are presently available, and I don't use the past hypothesis, I get terrible predictions, right? Everything is gonna just go immediately towards thermal equilibrium because I assume they're all Boltzmann objects, right? If I conditionalize on the past hypothesis, I wonder how much more do I get? Now, if I'm allowed to conditionalize on, say, the existence of zebras, where zebra is now like including all the scientific knowledge that's baked into what it means to me, right? Like, so I think there's a conflation in some ways between macro state and like macroscopic natural kinds or something, where like, what is it to be a zebra? And like the natural kind of being a zebra, essentially, I would say, includes like the history, the DNA, like all those biological facts. But now, can I take that to be the macro state that I'm identifying in phase space? If I do, it's going to be highly fibrillated, right? Because only certain micro realizers count as having any of that. And then a uniform measure over that may well give me all the exact right predictions. Question. Was that already what I was supposed to be doing? Certainly it's not directly surveyable, DNA, for instance. So I was kind of like, how much can we get just by using thermodynamics and not having to use like all the other things we take ourselves to know about the natural kind? I don't know if that's.
I think so. Here's a way to put my thought, or yeah, are we?
We might have to,
Okay,
yeah,
yeah.
maybe to take it later. So Carl and then it's actually Carl. My question was a bit related to this one and to what Michael said, but I always understood the Mentaculus vision and how it gets the special sciences out is involving a heck of a lot of conditionalization on other stuff. But in particular, one that hasn't been talked about yet in the discussion so much is, I always assumed it had to be a lot of macroscopic history over time and bigger systems, like maybe the whole planet Earth. We're going to talk about this, the life of living beings and things like that, because I mean, whatever the Mentaculus can give us about zebras, even if you put in a very good, rather microscopic description of zebras, it's not going to tell you whether a zebra is an apex predator or not, and so it's not going to make good predictions just on that basis about subsequent behaviors.
Yeah.
But we know the way zebras behave because of all this other information. So
Yeah.
I think that to make your point that you want to make in the paper about what's missing, you might want to say that there's a lot of conditionalization over historical information that's going to be needed if we're going to get the special sciences to come out at all. It's probable.
Yeah.
Think of economics, for example.
Yeah.
And then the question becomes, is it going to turn out that we're putting in basically
Right.
everything?
Yeah. Good. So that raises something I didn't really get a chance to talk about, but a kind of circularity worry about are all these kinds supposed to be results of the Mentaculus? So like if I am super Laplace's demon and I've got the past hypothesis and the measure, and then I have the current surveyable macro state, am I going to be able to then know all of the special science laws because I'm like, oh, these are the patterns? Does it just fall out? Or is it the kind of thing where I look around and do this kind of, I start as an embedded agent making assumptions about special sciences. I'm like, oh, there's zebras and there are people and there's all this stuff. And then I kind of do this reflective equilibrium, right? And then get back. And at the end, I have this beautiful, consistent story, but it's not like you can just derive one from the other. Like you had to start with a bunch of things that were like things you knew about the macro state, and they might be directly surveyable, or they might be other things you have to investigate. There's another question about the macro history, which is, I think, also related. Like, does that just fall out of the way that we've defined the Mentaculus, or is that something we also have to kind of build in? My guess is they're going to say the macro history is like further downstream. It's like more of a consequence with the present surveyable state and the past hypothesis assumption.
Section.
My question follows very nicely because it's gesturing to a circularity worry. But I noticed that you gave two options for where you can add to the Mentaculus. One was the past hypothesis, and one was I guess in how you define your macro states on phase space and basically making them a lot more fine grained and allowing for this speculation. So you didn't come out and say it, and I was wondering whether you agree with my intuition that your argument illuminated how a lot of information we put into how we partition, let's say, the phase space, what we thought was free before is not actually free. And to me, it doesn't neatly fall into the existing three components. I mean, the past hypothesis only does it for, you know, a small region of phase space. We need to partition all of phase space. It's not in the measure because the measure, you know, the measure has nothing to do with how you partition the phase space. And then, of course, there are the dynamical laws. So it seems to me like it's this additional input. And in the way you set up your argument, that strengthened this this worry that I had that if it's an additional input, it might actually lead to, you know, the circularity problem that probably.
Yeah.
So what do you
say about
that?
Great questions. Yeah, so I think when I was mentioning the past hypothesis, I wasn't thinking of putting anything more in there. I was just kind of wondering, maybe there's more we can get out that I haven't appreciated. But as far as the macro states go, I think, yeah, you can ask what do we know about the right partitioning of phase space? What are the right macro states? And the proposal I like is the thermodynamically specified regions. That's the right way to partition phase space. And then the ratio of functional states within that gives you this cool kind of complexity measure. But a different way to do it is to say, no, the macro state of being a zebra is actually much more constrained. So it's not that big thermodynamically specified region. It's got to have DNA, it's got it right. And so those are, I think, two kind of competing proposals. About the circularity, I also don't know, like, there's like the metaphysical worry about metaphysical circularity. I think ideally you do the past hypothesis, the measure and the dynamics, and then the special science regularities fall out, metaphysically speaking, for like Laplace superdemon. And then there's like an epistemic worry too. And I don't do epistemology, so I don't know. But I don't think there's anything too threatening about saying I just have epistemic access to like all this. And then make of that what I can, you know, and maybe I have to assume something like the past hypothesis, but there's, yeah, kind of, yeah, I don't know. But there might be more to an epistemic circularity that I'm not watching.
So then you would say, this more fine-grained proposal, whether it's fibrillating within thermodynamic macrostates or just having, macrostates with other vocabulary, you don't think that is an additional component of the Mentaculus, like they're still just.
Well, I don't know.
Or like
yeah.
to make the Mentaculus come to life.
Yeah. So I just don't know I don't know the right way to go. I tried to give a bunch of options and argue that if you think it does fall out in the way that maybe some people do, more could be said about how that works. And if you do need to add something like say, well, you'd better be conditionalizing on it being a zebra, then we should be explicit about that and then talk about what that looks like in phase space.
And one last quick question from you.
Sorry. I get a little confused sometimes in this debate because I feel like there's always a bit of ambiguity when we ask about what we mean by adding. Or the laws falling out. So yeah, when we ask like whether the special science laws just like really fall out of the Mentaculus, or whether we have to add anything to get the special science laws, like, I mean, like, just even to take like a simplified example, if you have, say you have the complete microhistory of the universe. You ask, do the laws of thermodynamics fall out from it? There's a sense in which, I mean, obviously, yes, you have the complete microstate of the universe, you have everything. But there's also another sense in which, like, I mean, it's like not obvious. I cannot do the derivations, etc. So here too, I feel like when we ask if you have to add anything to the Mentaculus, what are we exactly asking?
Yeah, good. I mean, yeah, these are just fabulous questions. So falling out, I mean, I guess I was thinking that it would be really nice for special sciences if there's, so it does seem to me that there are robust patterns at the special science levels. And with Craig, I'm thinking that, you know, all these scientists are like doing real objective metaphysical work. They're carving the world into real categories. There really are natural kinds like zebras. So it would be nice if there was a way to kind of like descry, if I may, those patterns from the Mentaculus. You say, look, this machinery, oh my gosh, we have robust patterns at this level of coarseness of grain. But you know, there's always the worry that you'll also have like gruesome zebra and you're like, all this stuff will fall out. And so I don't know. Then there are more resources though, because than just the particular microstate, because you also have the measure over all the possible initial kind of low entropy states. So that will get you a lot more. And, you know, there's kind of nice way of working out the counterfactuals for those. And so maybe you'd get more robustness at the special science level than if you were just restricted to like perfect information about an actual state.
All right, let's thank Heather for a great talk.
Those of us who are going out to the Friday dinner will leave from here in about 15 minutes. We have story time.
But I think we're all exhausted, so I'm not gonna say that. I want to say something about Heather's talk though, because as I was listening to it, This whole Mentaculus business has gotten way out of hand. It was a joke. Like many things, and if you don't say that you're telling a joke, when you tell it a joke, most other people don't understand it's a joke. I mean, I don't think it's a joke. I think really all that I thought was going on was Jerry was here, Fodor was here. I'm not going to keep what Jonathan thought I was going to do. I'm not going to tell record stories now because I'm too exhausted for it. But I did. I found the discussion that went on pretty confusing for me. Just then, not your fault, Patty. You brought up a lot of really important issues and points, but I was coming at it from where I was thinking about it is that in the photo world, you got the impression that when God created the universe, he had to not just make the physics, but he had to add something to the physics. And you sort of said that, and you were, not that you agreed with it, you said that might have been an idea that was floating around. It was that idea I wanted to combat. And I thought that statistical mechanics gave a tool for combating that against photo. That was really it. The idea that anybody could then look at these probability distribution and forget about doing biology or psychology or economics, that would be just totally, what to say, I mean, back, crazy. I mean, nobody ever thought that or anything like that. So the real issue for me is sort of more, I mean, really metaphysical. When God created the universe, did he, like Lewis thought when God created the universe, he had to say what the natural properties are and distribute them in space-time. That's what Lewis thought. He didn't agree with the counterfactuals and the laws can all come from that. Some other people think that God had to add laws to the universe to get that. Some people think, no, God added a bunch of counterfactuals to the universe and got the laws out of that. Or some people thought the properties were such that you can get the laws out of that. There are a lot of these different views around. I thought an interesting idea is something like what God had to do was just create the physics and the probability distribution. And that's it. Everything would come from that. I think that's still a viable program. And I think what you were saying is the things about to pursue that program, you want to give an account, for example, of how living beings could come up. And I think it's perfectly consistent with that, as David pointed out, and you agree that there would be, okay, but you want to know, well, what would make it likely? Okay, well, very little chancy things that happen all the way. I mean, who would have thought that I'd be sitting here now? But certainly my parents wouldn't have thought this, okay, or anything like that. So it was in the microphysics, but even the macroscopic said, and what Carl said before is completely right. When you conditionalize, you're going to have to conditionalize on a whole chunk of history too. So that's going to make this very different from when microphysics usually thought it was. Some people think microphysics will have to be conditionalizing on bits of history too, right? You think that, don't you? Yeah.
Yes.
Yeah. But most people don't think that.
People are wrong.
Yeah. But there's a lot, a lot of different ideas around, and that's what makes philosophy. Okay, I think it's not the time for stories, except. What's the best possible story? There's too many. I know. It just is a great place to be. And that's sort of just on. So end with that. We should go, we'll have dinner and we'll be happy and come back tomorrow when there'll be a bunch of other great talks. Janan's still there. She's full of sleep. Janan's gonna give a talk and Mike and Mark. What else is gonna be tomorrow?
Tim.
And Tim. But Tim's talk is called The End. I'm very, very fearful about what's gonna happen. Anyway, so thanks everybody.
Well, I think. Trying your best.
Like when you're getting.